All right, guys. Before we get started, guys, I'm feeling like these. I don't know how. I'm just trying to get your feedback on how the lectures are going. I'm not sure. I'm like making this sort of lack of face to face. Not 100% sure I'm making sense to you guys remotely. Um, any any feedback? Any thoughts? Anyway, I'm just kind of like feeling like the lectures aren't going great. So how are you guys feeling? Any brave souls out there?
I mean, the remote learning is just something that I'm trying to get adapted to as well. I think it's just kind of difficult, but it's not your fault, and I don't think that the lectures are going bad. I think I'm just having to revisit the material myself, again and again.
Yeah. My wife's going to USC, and this semester she's taking a DSP class that I think I was sort of just like looking over his shoulder and looking at the prof giving the lectures, and she thinks he's doing a pretty good job. And so I was talking to her, and she was suggesting, and I wanted to run this by you guys because just personally, I'm not sure how comfortable you're going to be or if you want to do this or not, but was to ask you guys to keep your like video on, and then for me to like bust out some questions, etc., to engage different people, or ask people to raise their hands and stuff like that, so it can be a little bit more back and forth. Because from my point of view, a lot of times I feel like I'm just giving like a one long monologue, and I'm not getting a feeling, am I like making sense or not, or just there's not a lot of like feed from just my benefit of I don't get a lot of feedback. Does that make sense? Do you guys want to try something like that for a week or two to see what happens?
That's fine. I think that's fine,
Yeah.
personally, for myself.
So what I'll do is I'll leave it up to you guys if you want to have your videos on. Today I didn't have my video on because I'm in my brother's house in San Diego and his spare bedroom, and it's a real mess here. So didn't want to distract you guys, but so I'll leave it up to you guys if you want to show up, have your videos. But what I'll do is I'll ask you guys to sort of raise your hands virtually. I think there's a way to do that, to like answer questions or whatever, or help me solve some example and that kind of thing, or maybe just call out people to like help me put problems. Yeah, San Diego is nice. Um,
Yeah. I actually live there right now.
oh, you do? Where are you at?
I'm in Rancho Bernardo.
Oh, nice, nice. My first job ever was in Rancho Bernardo at Unisys. So I used to drive there all the
Nice.
time. This is before, is that old I am? There was no 52 at that point. We used to have to go through Miramar, because my parents lived in La Jolla and my bro's in Del Mar. So I'm very fond of Rancho Bernardo. Cool. Okay, guys. Also, by I think Jafar got his wish, and I put in Project One. I think some of you guys were wondering about Project One. So I'm still, looks like, getting Cadence online is not going to happen this semester. We're getting like closer to it, but just like going very slowly. So looks like we're just going to focus on spice type simulation things, no layout and stuff like that. And I am suggesting, I have access to LT Spice, which is this thing from Analog Devices. You can just download it. You can use any spice you like. If you guys got P Spice, Microsend, whatever, everything's fine. It's just I don't have this is the only thing I got running right now. So if you guys, I mean, I'm happy to try to help you guys debug if you run into a problem, but it'll be more difficult. So anyway, I put up a LT Spice sort of user video up on YouTube and on Blackboard, so you can link to it, take a look at it. And so this project is really taking two of the problems from the midterm one and asking you guys to sort of simulate it. So this is kind of like a warm-up kind of project without a real complicated thing, but there's always like tricky things. Now, first, as a first thing, before we get into the problems, I wanted to say, like, one of the big, so there's like really two main issues that I feel like young new graduates have starting work. One of them is something hopefully we'll work on a little bit later, which is, you know, simulating. I think we've been touching on it, where you're just running simulation after simulation. When there are too many degrees of freedom, you kind of get pulled into this rabbit hole of simulation and no sort of analysis or hand calculation, etc. So like it's just sort of this endless loop of, you know, tweaking a parameter and resimulating. So that's like a trap right there. And I think this class, I think fortunately is addressing, you know, like doing some level of hand analysis to get a feel for it. It's important. The second thing, which I think is something I'd like to work with you guys on, and I don't know what state you're in, but like it's something we need to work on, is being able to present your ideas or results clearly. So, you know, there's the main thing that as you go to work, when you graduate, the main things that all your management will have in common, from your first line manager all the way up to the CEO of your company, will be attention deficit disorder. And so they will, you know, you'll have seconds, minutes, maybe 4 sentences, maybe a paragraph to make your point and or give them enough reason to keep reading. Okay, so basically presenting your project results or your results are something I'd like to work with you guys on, to try to, you know, maybe you guys are great at it, but it's not something I typically see. So anyway, for this class, so for the projects, I'm going to be like give you like a, you know, maybe like 50%, I think I said, of your grade is going to be like, you could have all the stuff done correctly and not have done a good job of presenting your results, and you could lose up to 50% of your points. Okay, so and I'm happy to work with you guys to get it to a level where well, I feel like it's good up to whatever standards I have. Okay, so the main things is the audience shouldn't have to go searching for what your point is. You should always have a point you're making. Let's say, you know, you're running here, problem one is, you know, you're simulating versus doing hand calculations, and you want to explain there's significant differences, right? So you're making a point here, doing this, and your results, you're telling something to your audience, and you want to make that clear. What a lot of people do, especially young people starting, is just they present a bunch of results. So they'll like overlap some waveforms, and they'll be like, there is no point of view, there's no discussion, they're not pointing to anything, they're not telling anybody anything. Okay, so that's very important to do. And in my experience, the key thing, because of this attention deficit disorder problem, is I always start my reports with what I call, and you've seen in sort of business circles, they call it the executive summary, which is probably going to be the only thing that most of your management will read in a, like if you have a 10-page report, most of the people reading that report are just going to read like the first paragraph. So you better summarize very well in that first paragraph and make it a separate section. Okay, that assuming that's all they read, this is what they take away with. And the rest of the report are more details that if they say they have a question about how you went about doing your whatever experiment or whatever work you did, they want to check to see if did that make sense, then they can refer to the further pages. Or if they want to look at the gory details of some current versus voltage values, and for whatever reason, they'll be able to find that in your material. But the key thing I want you to guys do in this first project is have this executive summary that's going to be a succinct representation of what you guys did for somebody who was got ADD. Okay, so that's the way to think. Okay, and one of the most important, like the main thing when I was sorry, I'll get off my soapbox in a minute here, but I didn't really understand sales until later on when I started working quite a few years in. But fortunately, I was always like a pretty decent sales guy. But everything, what I thought about sales, I was like looking specifically, like a car sales guy or, real estate sales guy, like a sales guy. Sales guy is how I saw sales. But in fact, everything you do at work, every time you try to get a promotion, every time you want to pitch an idea, every time you show somebody your results, you're doing a sales job. So I want you guys to think about that and approach all these things in that way. And, so salespeople are good at, dealing with people who aren't going to pay a lot of attention to them until they get a hook in, and then there's an opening. There's like interest developing. Okay. So that's sort of the approach I'd like you guys to take. Okay. Anyway, so the first problem is in the midterm, I asked you guys to use these, first level hand calculations with these values of oxide thickness, threshold voltage, and mobility, and plot the VDS versus IDS curves. And these happen to be from the TSMC 180 nanometer process. And so I'd like you guys to do the same thing, but now with simulations, okay? So, and the hint there is to use, I'm hoping you guys have at least used SPICE before, but just as a hint, use DC operating point analysis. And I have this kind of, I did a real quick and dirty. Can you guys see this LT SPICE screen?
No.
No. Let me see if I can share this. Let's see. So share. It's not much to look at, but can you guys see that? Yeah.
Yes.
Okay. So that's kind of what it looks like. Again, I have a couple of sample schematics on the blackboard. They'll have this. These are the SPICE models for the NMOS and the PMOS. So you'll have to refer to them. For example, if how do I do this? My Mac. Need to do a right click. Not my. Nope, I don't have my mouse with me, so I can't do a right click. But and if I did a right click on this is an NMOS transistor. You'd see that it's referring to a model name TSMC 180 nanometer N. which is what this model is. So now you're pulling this guy into that. And then it's doing this. I got a comment here because I was doing transient analysis later, but you see it's this DC operating point analysis and it's nested. So it's going through and stepping through the drain source of the PMOS and the gate source of the PMOS in a nested loop to create those models. So I was doing that for NMOS separately, and then the PMOS separately. And then, for example, let me see if I can, shoot, I wish I'd brought let me see if I can do this. Oh, how do you do a right click? Last hope. No. Edit, what? Edit, click to right click. Can't right click. Well, I think you guys will see it in the YouTube if you're not using this. So what you do is you hit, once you got your schematic done, you hit this run button, and then you can plot the currents. And so in this case, it'll be the currents for the NMOS and the PMOS. Okay, so that's problem 1. Anybody not used Spice before? Okay, that's good. Let's see. Okay, so that was that problem 1. Problem 2 is the infamous problem 2 here, which is this question about this. It's really, the question is really, the latch, I think is what confused most of you guys. The question is really about a NMOS pass transistor and, the capacitance values that are sitting on this node and the leakage current that you'll be seeing if this is the case. So here is whoops, I'm almost, let's see. So I separately had it sort of here, this circuit, and basically, you'll see this node, I'm getting a pulse input to the gate, pulse input to the input. I'm putting a 1.8 volts here, or trying to put a 1.8 volts here. I won't be able to because I'll get a threshold voltage drop from the NMOS pass transistor that does not like to pass a high value, as we looked at. So instead of a 1.8, we'll get 1.8 volts minus something here. And then after it's stored there on some capacitor value, it'll start getting drained off in time. So this value will start at, say, I don't know, whatever it is, 1.4 volts or something. And then it'll start at the time, after hundreds of microseconds or whatever it'll be, it'll start draining off and getting lower and lower. And then until it hits 1.3 volts, which the problem said is the lower limit on what is a good high value. So that's the project 1. I think that I'm going to make the due date not this coming Tuesday, but the Tuesday after that. I'm not sure when that is. Is that so this is
I believe that's the 3rd, right?
That's the 3rd. Okay. Does that seem good for you guys?
That's fine.
Yeah.
Yeah,
Okay.
Professor?
Yeah. Sorry, was there a question?
Could you repeat what you said? My audio cut out for a bit.
Sure. So the due date for the project 1 is going to be 2 Tuesdays from now, which we think is November 3rd, but I'll double check the exact date and just make sure that's correct, and I'll put it up on the Blackboard.
Yeah, that's fine with me.
Okay.
How about the Thursday?
Um,
After.
November 5th.
Let me check the date. Yeah, I think so. Yeah.
Yeah. Okay with me. November 5th. We'll make it November 5th.
Okay.
Okay. So let's do that. Okay. So now let's go to our start.
After election.
Oh, yeah. We'll see if there's anything. We might not have to worry about this project. There might be nothing left. So okay. All right. Whew. Okay, so back to the delay model. And like this is the part that was, I hopefully you guys got the gist of it. I wasn't very convinced that I was driving my point home, but basically the idea is that we are making an NMOS transistor. We're representing that as an equivalent resistance. And we haven't gotten to how we calculate that quite yet. But oops, I shouldn't be making any assumptions here. So this is just the source connection. And then this is the drain connection. And then there is sort of so the gate is just gonna look like a capacitor. And nominally, we just said these are all the same. They're close to being the same. In table, I think I want to say 8.43 in your book, you'll see the actual values for the TSMC 180 nanometer process, which is what we'll be focused on. They're not exactly the same, the drain capacitance, the source capacitance, and the gate capacitance, but for this very approximate hand calculation, we're just going to assume they're the same. So we basically said, okay, instead of this transistor, for the case of hand calculation of delay, we'll replace it with that. And then what we said was the equivalent for a PMOS is the same. So same capacitance on the gate, same capacitance on PMOS. So PMOS is sort of inverted here. So, so same capacitance on, I wrote through this badly. So this is the source, same capacitance on the source. And what we said, this is 2 times R equivalent. We said a PMOS has, excuse me, because the mobility of the holes is, approximately 2 to 3 times less than the mobility of electrons. A PMOSFET with the same size as an NMOSFET will have approximately twice the resistance, or sort of half the current sourcing capability, but the capacitances will be the same. Excuse me. And this is the drain. Okay. So we said we could replace these for our rough hand calculations. And again, within 7-15%, things like that, and not at every step in the transient analysis, but as a whole, when you're looking at the delay through the gate, within, again, 10, 15%, this hand calculation is surprisingly good. And part of the reason is because we're kind of fudging it because we are picking an R equivalent to make it look good. So, but it doesn't matter. It's basically, that's what you do. And so the nice thing is for every process, you only do this once, right? You only have to calculate your R equivalent. And in fact, you don't have to, but the book has it. But if you were going to do it, you'd only calculate this R equivalent once, and then you can use it over and over again to estimate delays through your gates. Okay, and so we went through example of a 3-input NAND gate, put in the capacitors, etc., and that's where we ended up. Okay, so that's where we were. So, so we had the capacitors, right? But then, how do we calculate the delay? Because if we have this thing, let me draw the resistors, or let me draw. Okay, so if I have, so I'm just going to try to draw just a few transistors here. Let's look at this bottom part. Okay, so if I was going to draw that bottom part, I would end up with a resistor for this transistor. It would have a resistor with R equivalent divided by 3, because this transistor, this 3 means is 3 times the nominal width, and that means the equivalent resistance is 1/3. Any questions about that? Does that make sense? Okay, so R equivalent over 1/3, and then so because it's 3 times the nominal width, this will be 3C. This switch, this is grounded. It's connected to ground. And then I'll have because it's 3 times the width, I'll have 3C on the drain. And then this next transistor up, we said it would be sensible to share the diffusions in the layout, to share these diffusions together. So again, just to draw it. So if this was going to be an active chunk in my layout now, I would have 3 poly gates, and this node would be connected to ground through some metal one, say. But then you see these transistors, so this guy and this guy, we'd learned how to merge their source drain, so we only end up with 1 3C value as opposed to both. So the drain and the source of the drain of this guy, would share its source with this guy, so we only have 3C and not 6C here. Okay, and then we'd have this R equivalent over 3 for this guy. Sorry, I'm switching colors here, guys. And then we got the next guy. I'm not drawing the switches. I'm kind of getting lazy here, but just give you guys an idea. Okay, so this is what we got. And then this last point had like a total of 9C sitting here, which was all the capacitors. So this thing, okay, will be this RC network here. The only break we get is because both sides of this node are connected to ground. We don't have to worry about this guy. But what we have is this RC network. If I was going to draw it like what it looks like ground, we have, R equivalent over 3. We've got 3C, then we have R equivalent over 3, 3C, R over 3, 9C. So the pull down will kind of look like that. And so this is, you can solve this, I'm sure, but it's already, even with just the one gate, it's getting to be a complicated RC network. So now this basically comes the next approximation technique that we use, which is this concept called Elmore delay. Okay, so it's all about approximation. Seems like with electrical engineering. And so this is, from, I looked it up, it's from some 1948 paper, whatever, some guy doing it, some guy, God bless him, W.C. Elmore, who did this analysis, and I didn't read it, but you just have to take it as like this mathematical equation that the delay through a complicated RC network like this, okay, is basically this equation. So in each step, okay, the delay is the resistance, the sum of the resistors times the capacitance at that node. So you have R1C1 plus R1 plus R2 times C2 plus R1 plus R2 plus R3 times C3, and so on and so forth till you get to the output. And if there were other branches hanging off here, you would just sort of follow the resistors and go up to that branch as well. So it's kind of a nice approximation technique for calculating the delay, the time delay through an RC network. So it's called this, Elmore delay, which is pretty convenient. For example, if I was going to do it in this case, right? So if I was going to look at this guy that we just drew, the delay, the Elmore delay, would be R equivalent over 3 times 3C, which is this guy, plus R equivalent over 3 plus R equivalent over 3. So that's this guy plus this guy times 3C plus R equivalent over 3 plus R equivalent over 3 plus R equivalent over 3 times 9C. So that would be ending up being the delay of like a low going transition. And what would that be? 2/3. So what would that be? That would be, you would end up with, this is 1 RC. This is 2 RC plus this is 9C. So this would end up being, sorry, RC. So this would end up being what, 12 RC delay. Okay, and we have the values for R, we have the value for C in this particular process. So you get like this really rough estimate for what a propagation delay would be for a falling transition through this 3-input NAND gate. Any questions about that?
Professor, could you go back to that slide real quickly? I didn't get
Sure.
all of it done.
This one?
Yeah. Oh no, the one before.
Okay.
Calculations. Thanks.
Yeah. Sorry, it's kind of a little busy there.
All right. Thank you.
Sure. Okay, so let's do this. Let's why don't you guys try to, I'm trying not to show you guys this thing, but try to, I'm sure you have it anyway, but try to doing this example of this 3-input NAND gate that's driving. This will be quite a bit of work here. So estimate the worst case rising and falling delay of a 3-input NAND gate driving H identical gates. Okay, so what does this mean? So the 3-input NAND gate, again, it's this guy. And they'll have its own, capacitances and resistances. Okay, and then the output of this guy connects to H other 3-input NAND gates. Okay, so what it'll see is H times the gate capacitance, the input capacitance for another NAND gate like itself. Okay, and the input capacitance, it'll be, so this was three, I think these were, the pull-ups were twos, I think. Twos. So each input here has 5C of equivalent input capacitance according to our model here, because each one will have on the gate will have 1C for a nominal width, and if it's 3 times the nominal width, there'll be 3C of capacitance. Okay, and since you're driving H of those equivalent, like, let's say you're driving 10 NAND gates, it'll be H times 5C will be what you'll be driving, okay, on your output. So basically, once the example is the maximum fall time and the worst case rise and falling delay, not fall time, sorry, rising and falling delay of 3-input NAND gate driving identical gates. Rising and falling delay is the propagation. So the worst case rising and falling delays these are the definition. Worst case rising, worst case falling is T, the propagation delay, rising, and propagation delay falling. Okay. So once you guys give it a shot at that, I'll give you guys like 5 minutes to give it a crack. Take a crack at it, and then we'll solve it together. Okay, guys, let's try to do this together. Okay, so let's look at the propagation delay falling first. Okay, which we kind of just did almost, but I remember the definition of delay falling was if I have time and I have voltage, we had the input, so this is Vn, was going to go from low to high. And the output, this is defined for an inverter, but again, all of our gates are going to be inverting gates. So actually, let me just draw that on top of then. So if I draw V out in red, it'll look like this, and then it'll start going down. So basically this, from the 50% point of the input to 50% point on the output, this, and then the output falling, this is our prop delay falling. And it's the worst case delay. That's why it's the propagation delay. The best case delay, or the lowest delay, would be called a contamination delay. In the case of a 3-input NAND gate, there's no difference between a contamination delay for the falling and the propagation delay for the falling, because there's only one way to get a falling output, and that's all three of these guys turning on. Okay, so for the propagation delay rising, again, it'll be like from the 50, I drew that badly, from the 50, so this would be from the 50% of point of the input falling to the output rising. So this would be T prop delay falling, okay. Now here, because we have 3 pull-ups, we actually can have 3 different rise times. Is it only 3 rise times? Yeah, I guess 3 different rise times. Okay, so the fastest rise time would be if your rising event means that all of these transistors turn on at the same time. Okay, so that will, if that's the case, how do I do this? Let me just erase this. Start again. So, yeah, okay. So you'll get sort of this thing redrawn. That's the fastest one, would be all three PMOS turn on. Or you could have 2 out of 3 turning on, depending on, again, on the inputs. And that'll be like another thing, but it'll take longer, right? Because you'll have higher resistance. And so that'll be 2 PMOS on. And the worst case scenario is only, let me do that another color. Worst case scenario is only 1 PMOS turn on, depending on the inputs that makes you have a rising transition. So the prop delay will be the case for the worst delay or the longest delay. So this thing with only 1 PMOS turning on is prop delay fall, and your contamination delay will be the 50 to 50 point for the sort of the fastest delay. So this will be the contamination delay fall. Okay, so on the rising edge, you can actually have things showing up sooner or later. And again, you'll see when we get to the sequential circuits mostly why the contamination delay could also give you a problem, this difference between contamination delay or propagation delay. But for this particular example, one, it's asking us for the worst case rising and falling delay, which means it's asking for propagation delay and not contamination delay. And so let's start with the propagation delay falling. So if you just redraw the pull down part of the circuit, we have 3 N MOSFETs. I just did this, but let's do it again. And each one of them is 3 times the width of the minimum to the output. And earlier we'd seen that this is at 9C. And so let me do this again. So we would end up having R over 3 So we've done this before, but does this make sense to everybody? Whoops. So this is on the pull down, okay, just for the NAND gate itself. Does this make sense to everybody? Why that's the case? Anybody have questions about that? Okay, if not, so that's the thing itself, but remember it's connected to a bunch of gates like itself. It's connected to H other gates. And each one of those other gates, we said, has an input capacitance of 5C. That's because each one of these inputs has 3 NMOS gates hanging off of it and 2 PMOS gates, each one of these inputs. So each one of these things you're driving is going to have 5C. So you're going to have an H times 5C load. Okay. So now we can use that's the drawing of the circuit, and now we can use the Elmore whatever delay. So T propagation delay falling is, so again, it's R over 3 times 3C plus R over 3 plus R over 3 times 3C plus R over 3 plus times, so on the top there's 9C plus H5C. Okay, so this is 12 RC plus 5H RC. Okay, or 12 plus 5H RC. Everybody good with that? Everybody get that? Anybody not get that? Okay, so that was the prop delay falling. Now let's look at the prop delay rising. So the prop delay rising is worst case delay, rising delay. Delay, which means the rising delay which you would get for the minimum number of PMOSFETs on. Okay, which in this case is just one of these guys on. Okay, so to draw it, we would end up with, there's a PMOS. The resistance of a minimum PMOS is 2R, but then the width of the PMOS for this NAND gate is 2, so it's 2R divided by 2, or just R. But the capacitance of that, well, anyway, the capacitance is capacitance on the output, which was 9C. Okay. Now, in a worst case scenario like that, look what happens, which is kind of for the most part, it's irrelevant. So, but I think for the sake of completion, we have it. So in this case, this guy, worst case scenario is this guy would be on, these guys would be off. So if this guy's on, this guy's off. And if these guys are off, these two are on, meaning that these capacitors, you can still, they're still hanging off of this node. So let's draw them in. So, but this is the node where we're interested in the delay. So we're interested to that node. But if you was going to draw the whole circuit, I would also, let me draw them in red, or maybe, green. I would also draw the R divided by 3. This is the PMOS, the NMOS, 3C. Okay, so I drew that for the sake of completion, but notice if you're doing an Elmore delay calculation, you just are doing this resistor times this capacitor. Because of this resistor here, you don't really see these things because the Elmore delay is only the resistor network to the output that you're interested in. It doesn't, it's not affected by these other branches. So basically ends up being T propagation delay rising. Whoops, rising is, this is just R. Okay, it's, oh, sorry. I also have my loads. So this is, we said we'd have a fan out of H5C. So H times other gates. Okay, so in total, we'll end up with 9 RC plus 5 HRC. So that's equal to 9 plus 5H RC. Everybody good with that? So anyway, that's how you do the calculation. And, I guess if you're going to draw any conclusions from this is that, when you have a NAND gate, notice that even in a worst case scenario, the rising propagation delay is less. This was 9 plus 5H. It was 12 plus 5H for the falling. That's because the NMOS transistors are in series, so falling is going to be slower than rising. Even in the worst case of rising and in the best case of rising, falling is going to be quite a bit slower than the rising. Okay, so that's what you get out of this. Okay, and then the other thing is notice that in each case, we have a component of delay that's just, for example, this 9 RC, this first term, is just a device itself driving its own parasitics. So even if it was driving nobody else, so if H was 0, you still end up with 9 RC of delay as this thing is charging and discharging its own nodes capacitances. And so that's one component. And the other component is just, the input of other devices, which is this 5HRC. And so what we're going to define is these two definitions, which we'll use in a little bit here. We call the parasitic delay the delay of just the device itself charging and discharging its own capacitors, and the effort delay, the delay to charge and discharge whatever it is, whatever other components you're driving, which are the other gates. Now, whether there'll be other gates like yourself or other type of gates, period, depends on the design. But that's called effort delay, and driving yourself is called the parasitic delay. Okay, so now we can do the same thing. So with the same example, we can do the contamination delay. So it's asking us to do that. Let me just do that real quick. So maybe I just use these results. So if I was going to look at the contamination delay, what would we look like? So this is T contamination delay rising. So this is best case. So in the best case scenario, or the fastest case scenario, all these three devices would be on at the same time, meaning that you would have R plus R plus R. Your resistance goes from just being R to basically, like R over 3. So it would end up looking like this. So this would be 2R over R, 2R over R. Okay, so you'd end up with, what would that be? It'd be R over 3 times 9 C plus 5H R over 3 C. Is that right? Yeah. So be 3 RC plus 5/3 H RC. Did I do that right? Change my H to case. So 3 plus. Okay, so that's our contamination delay. So that's the shortest delay on the rising edge. Okay. Okay, so main components, blah, blah, blah. All right, so now let's see what I want to say this. I think basically, this is saying there are ways of, by certainly, as you can see here, it's describing why we only get 3C and not 6C here. It's because we've merged these source drains for the pull down. But in addition to that, it says that, we can even do better than 7C here by merging these drains. I'm sorry, about 9C, you can get down to 7C. So it just depends on, good layout optimization. You're reducing your parasitic delay. Okay, and this one is doing these stick figures, suggesting that we could do the layout both ways. And of course, I believe this layout on the left would be better, because you can see that the capacitance on this output node is very important. Okay, and the way this is laid out, it'll see this diffusion and this diffusion. But in this case on the right, so instead of seeing this guy and this guy only, you'll see this guy, this guy, and this guy. So you'll have, roughly about 1/3 more capacitance on that node. And you don't want that. Okay. All right, so that's where we are with this thing. Any questions about that? No? Okay, so let's see. Let me look at the next slide. So let's, I think I'm gonna stop here for today, because, this is like starting at the next slide set. It's a continuation of the delay ideas. It's something called the logical effort approach, which is sort of an approach to help you use this methodology of these sort of hand calculations to optimize delays through more complicated circuit block. So it's a continuation of what we just talked about, but it is a sort of a new section. I think we could just, it's 8:07, so we can stop here and pick it up again on Tuesday from this point. Any questions?
Professor, so they do for project in September, okay?
Sorry, Jafar, you're breaking up. Can you say that again?
Yeah, when is the exactly due for project? November or third one? The fifth one or third one?
Okay, let me pull up my calendar. Let's see. So it will be November 5th will be the due date.
Thank you.
Okay, sure thing. Any other questions, guys? If not, have a great weekend and take it easy. Talk to you guys on Tuesday.
Thank you, Professor.
Thanks.